Welcome. In this tutorial we'll be looking at some basic matrices. We'll examine how to use a CAS calculator, reviewing the basics of an identity matrix as well as that of permutation matrices. So first of all, let's examine the identity matrix, often given a capital I as a symbol. Before getting too deep into identity matrices, most students would know that with matrices the order in which you multiply is really important. Multiplying a matrix A and a matrix B will not give you the same result as multiplying in reverse matrix B with matrix A. Generally speaking, this process of multiplication is not commutative. That is, you can't change the order without some kind of impact. Let's have a quick look at the examples we have here on our CAS calculator. First of all, we'll enter in our basic matrix, a 2 by 2. So matrix A was a simple 1, 2, 3, 4. And we were multiplying that little asterisk symbol with a second 2 by 2 matrix, which, surprise, surprise, was 5, 6, 7, 8. Oops, 7, 8. Now when we multiply it together, there's our result. Let's try the reverse order. 5, 6, 7, 8. Multiply with the asterisks. 1, 2, 3, 4. And no surprises, we get a completely different answer when we reverse the order of our matrix. So down here we've said that the product of matrix A and matrix B does not equal the product of matrix B and matrix A. This is what we mean when we say it's non-commutative. Now there is an exception to this rule, of course, and that is when you multiply with an identity matrix. So let's go back. This time it's something a little bit different. We'll try a define function whereby we can recall a matrix over and over again. There's two ways of doing this. One, you can hit this little book symbol and hit the temp here, the term define. And I can define A to be equal to, open up my matrix, 1, 2, 3, 4, and enter, and that's done. Or I can just type in the word define. In this case I want to use I, the identity matrix. And as you recall, an identity matrix is a square matrix containing only zeros and ones, with the ones down the main diagonal going from top left to bottom right. Now they're both defined. So if I want to multiply matrix A, and you see when I press A now it comes up in bold, saying that it is defined, multiplying it by identity matrix I, what we find is when we multiply by the identity with a 1, 1 on the main diagonal, A remains the same. A times I is exactly the same as A. It's just multiplied every value by 1, effectively, 1, 2, 3, 4. Now if I were to reverse the order of that multiplication, lo and behold, I get the same values, the 1, 2, 3, 4. So as we mentioned, an identity matrix is the only that I know of matrix where you multiply in either order with another matrix, the second matrix, and you get the same product. Effectively, as I said, it's like multiplying by 1. Okay. Permutation matrices. Now a permutation matrix is again a square matrix. It's also what we call binary in that it consists of zeros and ones. So really it is an identity matrix with the rows or columns shuffled around. You'll notice in each one of the three in this example, there's only a single 1 in each column and a single 1 in each row. No matter which one I look at, you only count one number 1, and the rest will be zeros in each column and in each row. That's one of the rules of being a permutation matrix. So we want to look at how we can use a permutation matrix to create a column permutation, an effective swapping of columns when we multiply, and a row permutation or a swapping of rows. So I've got an example here with two matrices, one of which is a standard matrix, matrix Q, and it's got the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a 3 by 3 matrix. And then a permutation matrix with zeros and ones, only one within each column and a single 1 within each row. So let's go back to the calculator and have a go at this. So first of all, I've shown you the define function to store matrices. There is another way, and by the way, this is how we load up a 3x3 matrix. 3x3. Whenever they're larger than a 2x2, we need to specify the dimensions. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, what I can do is store it, so I can use a control and the vary button, which gives me a store, and I might store that, say, to letter Q, and that is now done. So whenever I type in the Q, up will come that number. It's another way of storing away the data. So in this case, let us do another store. That was matrix Q. Let's now do our permutation, a 3x3 matrix. Permutation matrices have to also be square. Can't remember if I've mentioned that yet or not. And 0, 1, 0. So we're going to store that, control var. We're going to store that as a P for our permutation. Okay, so let's have a look. If we go back to our original slide, here's our original Q with a 1, 2, 3, 4, 5, 6, 7, 8, 9. Easy to remember, and there's our permutation matrix. In this case, we're going to multiply the Q by the P in that order. Our original 3x3 matrix by the permutation. So Q multiplied by P. Hit that, and you'll notice we've now got what appears to be a mucked up order. Let's have a look. There's our original 1, 2, 3, 4, 5, 6, 7, 8, 9. And now we've got 2, 3, 1, 5, 6, 4, 8, 9, 7. It seems to be a real mess. Is it the same? 2, 3, 1, 5, 6, 4, 8, 9, 7. Yes, it is. So what we've done is effectively taken the column 1 in Q and moved it across to column 3 in the product of P times Q. And what was column 2 has been moved to column 1, and what was column 3 has been moved to column 2. That's why it looks all marked up. Now, those of you who are astute and understand elements within matrices might pick up some kind of pattern here. This 1 is located in the first row and the third column, so it has the element reference of P, 1, 3. And if we use that as a key, it suggests that column 1 will be shifted to column 3 when we multiply it by the permutation matrix. And in fact, 1 has moved to 3. This has a reference, this element, of row 1 and row 2 and column 1. So it can be used as a key that we're shifting column 2 from the 2 in the first reference, the element, to column 1, and 2 did move to 1. And then finally, we've got row 3, column 2. Row 3, column 2 for element P. So it's moved column 3 to column 2. You can read this permutation matrix, if you like, as a shortcut or a key or a grid in terms of determining where each column will move. Let's look at a second example. We've started with 3, 1, 2, minus 2, 4, 7, 0, negative 1, and 8 as my matrix, 3x3. I've got a new permutation matrix, and I multiply Q by P in that order. And what's happened here? We've got our first 1 is in row 1, column 2. So that means our first column will move to column 2, using this as a key or a rule. 1 to 2, column 1 to column 2 is our movement. Our next one is in row 1, column 3. So that means row 2, column 3. That means column 2 in our first matrix Q will move, as the key suggests, to column 3. So it's moved across. And then finally, our last one here is in row 3, column 1, which means what was our third column in the matrix has moved to our first, using our element key of 3 to 1. It's a nice simple pattern for column permutations. We can also use our permutation matrix for a row permutation, and as you would suggest by the name, this involves switching the rows around. However, to do this, we must multiply our 3x3 matrix by our 3x3 permutation in the reverse order. This has its own little unique characteristics, but let's go back and have a look. So earlier we defined Q as the 1, 2, 3, 4, 5, 6, 7, 8, 9. And we defined our permutation as the 0, 0, 1, 1, 0, 0, 0, 1, 0. Sound like Bender out of Futurama. But anyway, I digress. Let's go back to it. In this case, we wanted to multiply the P with the Q in that order. So if I have P and multiply that by the Q, hit enter, and I end up with 7, 8, 9, 1, 2, 3, 4, 5, 6. Again, that looks randomly all over the place. Let's go back. We expected 7, 8, 9, 1, 2, 3, 4, 5, 6, but what we find is now we've moved our rows. The top row has moved to the second row. What was the second row has moved to the third row as a final, and what was the third row has moved to the first row. Now the pattern does not look as obvious, but again with the elements we have a key. The first element, 1, is in row 1, column 3. Row 1, column 3. Now when we're looking at row permutations, because of the process of the multiplying a 3 by 3 matrix with another 3 by 3 matrix, we do the reverse. What was in row 3 moves back to row 1. So here row 3 moves to row 1 in the product. Our second element with a 1 was row 2, column 1. So in reverse again, what was in row 1 now moves to row 2. So this purple row 1 has moved to row 2. Our third and final is in row 3, column 2. So again, reading in reverse, what was in row 2 now moves to row 3. The green, what was in row 2, has moved to row 3. It's a little tricky, but it is doable. Finally, another example. Let's have a look. In this scenario, we've got our 3 by 3 Q with a different 3 by 3 permutation matrix. And so let's look at the key as a shortcut. Row 1, column 2. So what was in row 2 will move to row 1. So the green in row 2 has moved to our answer product of row 1. Our second 1 is in row 2, column 3. So what was in row 3 will move to row 2. 3 goes to 2, as predicted. And a final 1 is in row 3, column 1. So what was in 1 now moves to 3, using the reverse order. So what was in 1 now moves to 3. Our prediction using our permutation matrix is correct. I hope that's been useful in terms of the basics of the calculator, identity matrix, and the row and column permutation matrix. Thanks for viewing.